Figure 1 shows the central vertical cross-section, A, B, C, D, E, F, A, of a vase together with measurements that have been taken from the vase. The horizontal cross-section between A, B, and FC is a circle with diameter 4. That is implying that this is a volume of revolution question. We are taking this curve here and rotating it around the y-axis. The base ED is horizontal and E is vertically below F, D is vertically below C. And then CD is modeled by these parametric equations. O is the fixed origin as shown in figure 2, and we're asked to determine A and B. So what we can see is that D is going to have x coordinate 2, because here's my line of symmetry. The diameter is 2, so the diameter is 4, so the radius will be 2. And then the y value is going to be 0 here. And then for C, again it's 2, but then it's 7. And we can use these and sub them in. So I'll sub in the 2, 0 to begin with. I'm going to get 2 equals A plus 3 sine 2t, and 0 equals B cos t for that point. Now I can divide through by B and solve cos t equals 0. T's got to equal pi over 2. Remember, t only varies between 0 and pi over 2 here, so there's no extra solutions. I can then sub that back into the top one, and I'll get 2 equals A plus 0, because sine pi is 0. So there we go, we found our value of A. Now I can't determine B from this one, because it just cancels out. But what I can now do is sub in my C. So now 2 is going to equal 2 plus 3 sine 2t. Actually, that means that 3 sine 2t is 0. So sine 2t is 0, so 2t is going to be 0 or pi. And then t is going to be 0 or pi over 2. That's what we're going to need to get that value of 0. Now, we've already dealt with it equaling pi over 2. So actually, t is going to equal 0 here. And I haven't used the b yet. So I can say that 7 is equal to b cos 0. So b is 7. And let me just also highlight once more that, yeah, here t is going to be pi over 2. And here t is going to be 0. We're going to be using that in a minute. Using algebraic integration, show how you're working, determine according to the model the volume of the vase, giving your answers to the nearest centimetre cubed. Okay, so we're going to split this into 2 parts. First up, we've got ourselves a cylinder. And the volume here is going to be pi r squared h, pi times 2 squared times 4.5. That's 4 times 4.5, we get 18 pi. Now it's for this bit here. So we're going to take this curve at the bottom and rotate it around the axis, creating these little cylinders, which we're then going to sum up. So I'll call that, maybe I should call that V1. And this is going to be V2. So V2, now remember, to get a little cylinder, we are going to be doing the radius, which is x squared. We're going to create like a little height, dy, and we're going to have a pi in there, and then we're going to be summing them all up. So this is our formula for the volume of revolution around the y-axis. And for us, we're going from, we're going to be changing this in a minute, but we're going to be going from y equals 0 to 7 as we sum up the axis. But we're going to be doing this parametrically because the equations are defined parametrically. So we'll replace x by a, so 2 plus 3 sine 2t, and we are squaring that. And then dy is actually going to become, so we can replace dy by dy by dt, dt. We're using the chain rule here to do that. And then y is 7 cos t, so dy by dt is going to be minus 7 sine t. Okay, so I'm hoping I feel like actually I've done too many steps there. Let's put one extra step in. So it's going to become x squared dy by dt dt. This is just like when you're dealing with it in A-level maths. It's just there's an x squared there. Okay, and then I've substituted in, and I'm integrating now with respect to t. Okay, and this bit is really important. So we need to use the t value that is associated with 0 at the bottom. Actually, that is going to be pi over 2. And the t value associated with 7 is 0. So the upper limit is lower than the lower limit. You should have seen that before. That is not, that is absolutely fine. Now, what we can do is two things. When you swap the limits round, you actually make it negative. If you have the integral from a to b, it's the same as minus the integral from b to a. Because all you're doing, remember, is you're putting your limits in. And normally it would be like you put b in to your function and then minus a. But if you do function a minus function b and then make it negative, we get the same thing. So we can do that, and we can get rid of that negative on the 7. So it's going to become 7 pi 2 plus 3 sine 2t sine t. I mean, this integral is not easy at all. There's a double angle in there. And we're squaring it. Thought about that for a second. So there's some groundwork to do here before we get it in the right form. It's quite a bit. Okay, let's expand the bracket. 4 plus 9 sine squared 2t plus 6 sine 2t plus another one, so 12 sine 2t times sine t. All right, next up. Okay, let's multiply through by sine t. And at the same time, I'm going to deal with the sine 2t. Don't forget, sine 2t is 2 sine t cos t. So I will get 2 sine t cos t here, which I am squaring. Then plus 12 sine t times 2 sine t cos t. Okay, 4 sine t plus 36. Now, maybe I should have, this here is actually going to equal 4 sine squared t cos squared t. Don't rush this bit. I'm going to get 36 sine cubed t cos squared t. Then plus, actually write down here, plus 24 sine squared t cos t. Okay, now this is absolutely fine to integrate. Actually, this one's not too bad either. If you practiced it enough, it's reverse chain rule, because when you do d by dt of sine cubed t, you bring the 3 down, you lower the power on the sine, because that's the outside part, something to the power of 3. We times by the derivative of sine, we're going to get 3 sine squared t cos t. So we can do the reverse here in a second. That's good if we can get it. So we've got like a power of a trig function times like the opposite trig function, but no power, then we're sorted. So the problem at the moment is this one here, because we've got a cos squared. We don't get an immediate answer from this. This isn't going to become sine to the 4 or anything, because when you differentiate sine to the 4, you don't get a cos squared coming out. And for me, this is the hardest part of the problem, potentially the hardest part of the whole paper, I think. It all depends, of course, how much practice you've done of these. You might look at it and be like, yep, I know what to do. So what you do not do is try and replace cos squared by 1 minus sine squared, because then you're going to have to integrate sine cubed and sine to the 5, which is possible, but it's going to be like horrible. It's going to take a long, long time. Instead, we're actually going to replace sine cubed by sine and then sine squared. So sine cubed t cos squared t is actually going to equal sine t and then sine squared t, which I'm going to replace by 1 minus cos squared t. And what we actually end up getting is sine t cos squared t minus sine t cos to the 4t. See, I've now got it in this kind of form. Okay, we're ready. So that's like just a little aside. So now I'm going to get 7 pi integral pi over 2, 0. Before I integrate it, let's just write this down. So 4 sine t plus 36 sine t cos squared t minus 36 sine t cos to the 4t. And then, of course, I've got my plus 24 sine squared t cos t. Okay, that is looking good. We're ready to integrate. So sine integrates to minus cos. I'm going to get minus 4 cos t. Here, I'm using inspection / reverse chain rule here. I'm going to get cos cubed t. Now, when I say inspection, I mean I'm going to like differentiate this back and just check what I get. So I would times through by 3 and lower the power. And I times through by the derivative of cos t, which is minus sine. So I need to make this minus 12 for it to work out. You could alternatively take your 36, divide through by 3, and times through by a negative. Okay, whichever works. But I would recommend just differentiating it back and checking it works. And I'm going to do exactly the same for this one here. I'm going to get cos to the 5t. Now, when I differentiate this, I'm going to get 5 cos to the 4t sine t with a minus, sorry. So now it's going to become plus 36 over 5. And the last one is the one I spoke about the most. I'm going to get sine cubed t. I just need to divide through by 3. I'm going to get 8 sine cubed t. Okay, differentiate it back. We will get 24 sine squared t cos t. Okay, that's the hardest bit of the question because actually subbing in the limits now is going to be very quick because of the nature of what they are. When you find cos of pi over 2, they're just all 0. So we get a load of zeros here. 0 plus 0 plus 0 plus 8 sine cubed of pi over 2. Actually, sine pi over 2 is just 1, so we're going to be getting 8 here. And then we're going to minus. Now, cos of 0 is 1, so I'm going to get minus 4 minus 12 plus 36 over 5. And then sine of 0 is 0. Okay, at this point, I would, yeah, I'd get my calculator out. We end up getting 7 pi times 84 over 5, which is 588 over 5 pi. And then the final volume is the 18 pi we had at the beginning. Remember, it's a long time ago now, but we worked out the volume of the cylinder at the top. And now we've worked out V2, so it's going to be 18 pi plus 588 over 5 pi. And this ends up being 135.6 pi, if I'm leaving it exact, but now it's a model, remember, let's write it to 3 significant figures, 425.999, 426 centimeters cubed. Wow, fantastic. Okay, that's hard work for those marks. We are on the last question, of course. Finally, we're asked to state a limitation of the model. What have we assumed that might not be true? And I just went with it. We assumed the vase is perfectly smooth, whereas it might not be. It might be like jagged in places that would affect the volume. Some other options is you could say it might not be perfectly symmetrical, measurements may not be accurate, equation of the curve may not be suitable model for the CD, thickness of the sides has not been considered, the base might not be completely flat. So those are some options. Okay, great.